Hey, we have another integral here on the board. We have the integral from 0 to pi, cosine x, cosine 2x, cosine 3x, cosine 6x dx. Okay, now you may notice this is really similar to an integral that I did about a week or so back. And I think that's where I got the idea for this is the other integral we did kind of simplified pretty easily. The thing that's interesting with this one is it's a little more difficult than the integral that we did last week. And I think some of the methods that we used on the previous integral aren't going to really work here. So first off, let's look at the methods that I used in the previous video. I think what I did was something like a substitution u equals pi minus x. And this substitution actually simplified it pretty nicely. I think some people in the comments tried something like pi over 2 minus x, and that worked nicely. There were situations where you could use even odd functions. I didn't look at it too deeply, but it didn't seem like these methods were going to work or not as easily. So I think this might be messy, and I'm not going to go this way for this integral. Now the other thing we could try on this is just the different angle formula. We'd have to apply it multiple times because the different angle formula allows us to group like by 2. Let's just look at that formula really quick. So here we have this different angle formula, and notice this works on 2 cosine functions. So we could take like cosine x, cosine 2x and apply this, and we get like a half cosine x plus cosine 3x. We do the same thing here, but then we need to multiply them together and apply it again. So this method would work fine just applying this repeatedly. It's just a little tedious, so I was trying to avoid that, but this is a fine method. Now what I did for this is actually something closely related, and let me just look at that and let me show another formula. Okay, so now on the board I have this formula that you don't see very often. It's actually different angle product of sum for 3 terms of cosine. And notice even at 3 terms it's already getting pretty messy, right? It's kind of getting long. But all we have is we go from a half to a fourth. And then kind of like this, we end up with 4 terms instead of 2 terms. And notice we have every combination of sign. So it's just like each of these terms is a little different based on the sign. Well, the thing here is this is 3 terms, but we're actually dealing with 4 terms. So let's look what would happen when we have 4 terms. Okay, so now with this formula, we do have our 4 cosine terms, and this is actually the same case as our integral. And now we go from a fourth to an eighth, and we're going to have 8 terms. I'm not going to bother writing them all up. And of course, these formulas just come from applying this over and over again. So there's not any special magic here. It's just like you can get to this, you can get to this or this just by applying the different angle formula over and over again. So notice that we actually have 8 terms here. And if I write that all out and then we integrate that, I mean, it's not going to be horrible, but it's going to be pretty tedious. So, and that's actually what I was trying to avoid by not using the different angle formula. Well, it turns out that we can actually avoid this, and we can kind of avoid the real details of this. The way we'll do that is we'll just put a 1 there on the coefficient, and we'll notice that the coefficient on the angle here for these 3 terms, 1 plus 2 plus 3, that equals 6, and we have our 6 right there. So one of these 8 terms will be something like, let's just say cosine of A minus B minus C minus D, because just like this, we're going to have every combination of sign. Well, let's call our 6x A. This will be B, this will be C, this will be D. Well, when we calculate that, we're going to have cosine of 6x minus 3x minus 2x minus x, but this is actually cosine of 0x, and cosine of 0x is cosine of 0, and that's just 1. So knowing that one of our terms is going to be just 1, we can rewrite this. We can take our 1/8, same bounds. One of the terms is going to be 1, but then what about the other 7 terms? Well, I'm not going to bother to calculate those, but we're just going to have a bunch of values that I'm not going to worry about. So we'll say n1x, n2x, and this is going to go to cosine n7x. Okay, and from here we'll just integrate this thing. So we'll have 1/8 out front. Integrating 1, we're going to have x. So then so then for this term, we're just going to have sine n1, whatever that is, divide 1 n1. And then we're going to have another one like this, all the way to n7. And we just need to evaluate this from 0 to pi. But then here's where we get some really nice simplification, just looking at what happens when we put pi in for all these n terms. And keep in mind, it's important these coefficients are integers, because when we add everything together, we still have integers. So when we enter a pi in here, any n of pi, all those are going to 0. But then again, when we enter a 0 in here, sine of 0 is going to be 0. So every single one of these is going to 0. We don't have to worry about that part. So then just to clean this up, we're just evaluating 1/8 x from 0 to pi now. We plug 0 and we get 0, of course. We just need to plug in pi. And so for our solution, we're going to have just pi over 8. So I thought it was interesting that even though we couldn't use a lot of those methods that we used in the previous video, it still it still was a case where you could really do this one very quick, and it ended up being pretty easy to simplify. Anyway, let me know if you had some alternate methods. I'd be interested to see if people solve this a different way. And we'll stop it there. Thanks everyone for watching today. Please like and subscribe. Have a great day.